Hello, I'm Philip Meyer, I'm an electronics engineer, and in this video we will try to improve on our flyback experiment. You remember my last video I made this flyback secondary coil out of basically Tesafilm, epoxy and these nice self-fusing rubber tape. But that didn't work out too well. And in this episode I want to try to make another one that is a bit smaller and will fit better. Yeah, basically that was the only problem I had with that. It was just too big and I couldn't make enough layers on it to get the right voltage, and it was too big and it started to have a bit corona inside. And this time I want to solve these issues. And yeah, let's see how far we get this time. Okay, this is my starting point now. I already did some work here. This is the old flyback coil I made. You've seen that in the previous video. I already taken this apart. Have taken this apart again, and in order to make it more safe, and yeah, I decided to put a shield in front of the horizontal output transistor. That's because I want to not only to insulate that even more, I also want to shield it from the electrical field coming from the flyback. I mean, call me paranoid, but I mean, this is a self-made thing, and should it ever decide to do something harmful, arcing or whatever, I want to have a metal plate here that catches arcs on our electrical fields, so that should be pretty safe then. And I also did a similar thing here. You can see the copper plates there. I want to mount this right here, right in front of here, to have that shield as well, and maybe I will wind some turns of these rubber tape around this. I don't know yet. This is the plan, to make it more rugged and more solid in the end. Because the last thing I want is that it arcs somewhere into the electronics, and because then that would be game over. And once it's built in and hidden from my eyes, I cannot see it anymore. And if should there ever be problems, I want to have the rest of the electronics well protected. This is my new winding base. It's of course much wider than the previous one, and I don't have these the guides at the side. I just leave that away because I think I can make it without any problems. And after that I will seal it. Well, the same concept. I just put epoxy on both sides, and that will be it. I mean, this is from cardboard. It's a cardboard piece from these kitchen wipes. Oh no, it was aluminium foil in this case. And this is said aluminium foil around it. And I did it the same way like last time. I have the wire running in here and the little solder dot already prepared, and that also had a bars in cyanacrylate to make it more stable. So I will do the windings around this, and as you know from the previous video, that's what Daniel Auerbach suggests. 26 layers by 68 windings. So let's see if I can manage to put all of them on it and have it small enough, because I really don't want to have it to grow more than, I mean, a centimeter would be okay, but centimeter, that would be the max. So I hope I can make it very compact this time, so we will see. let's try. So it's now 3 turns later, and of course I'm having again problems with the coil and the uneven surface like last time. And my idea this time to cope with that is to use office tape to a few layers. I mean, it could be, I don't know, it's like 20 or so, to equalize the surface. And yeah, that's done in the hope that the wire will not flip away again. So yeah, that should do it. The only downside with this is if you cut it, if you trim it, then you will have to look carefully out for these turns that jump over here, for the basically the connection in between the individual layers. So you have to be very careful not to hurt this with the scissors or whatever you use for cutting. Yeah, this is very tape consuming, and I think I will not make it today. I will have to go to the shop tomorrow to buy new office tape. Yeah, and by the way, I use teaser, and I recommend teaser, not the cheap stuff. You should, for these, I mean, this is when it comes to high voltage, and so you should choose the original. There's just no other way. The other cheap stuff, I don't know how well that might work. So yeah, all my office tape resources are now used up, and I will have to go to the shop tomorrow to get new office tape. And yeah, I think that's it for today, and this is now 10 layers. So let's measure how thick that is to at least get an approximate estimation if this time that will be a success or not. So this cardboard piece is about 2 millimeters thick. So let's subtract 2 now. Careful. I think that's it. It's about a little more than 4 millimeters. So yeah. So if it goes as worse as it can get, let's say need 5 millimeters, and so that's would be 20 layers then, and so yeah, this would be about 26 then, and so the coil would have a dimension of somewhere like this, so that wouldn't be too problematic. I mean, if I compare the size here, okay, there's these rubber things, the rubber stuff around it. Yeah. Yeah. Could be somewhat tight again. Okay, yeah, anyway, this is with rubber, and I don't really remember how thick this was. I guess it was like this. So yeah, it could be that it could be the same size again, unfortunately, but we will see. I cannot say for sure, of course. Maybe I managed to pack it somehow tighter and make it fit, but oops, that's still on the, so that's, yeah, I mean, we will see what happens. So maybe I will skip a layer or two then. Yeah, we have to see, we have to try. I mean, yeah, okay, that's it for today. We will see tomorrow, of course, and then we will hopefully have some results. So this is the full thing now. I've made the full stack of Yeah, the last one is missing. So the full stack of 26 layers now on the coil. Yeah, that was a lot of hard work. So this right now consists only of tesofilm, so that's no epoxy inside this right now. Yeah, so that's basically a thick roll of tesofilm with some copper inside. And the technique to give it some extra turns just outside, just wrap it around just like this outside to equalize the surface here turned out to work very well. I mean, you can see by the rings here where I did it. I did it not after every layer. I did it after about 3 layers. I equalized the surface again, and then it was easy to continue. So that worked out pretty well. Now I will seal the sides with epoxy. That's what I do, and I also want to check if that is working properly. Yeah, it fits just right, I think. So here's the shields I made for that. They also fit. I hope they will still fit once I applied the rubber coating with the self-fusing tape. And here the distance to the horizontal output transistor is quite okay. It's a little bit tight, but I think that will be okay. That will be fine, I think. So yeah, let's seal it, and then we do the next steps, I think. So yeah, I have the first layer from at one side on. Maybe I do a second. And what you also can see is there are some bubbles in there. And yeah, they're coming up through the glue now. Or there's a big one. I just popped. Oh, I don't know. No, it didn't pop yet. The problem with this is this is just phenomenon because there's still some air inside the coil, and in an industrial environment you would use a vacuum pump. So you would put that in epoxy, liquid epoxy, and then you would put it in a vacuum chamber, and all these bubbles would be sucked out. I don't have a vacuum pump here in my lab, so I have to just live with it and hope that the bubbles there will not have any negative effect. But I think there's a lot of this insulation distance this time, a lot more than on my previous coil. And yeah, for those who are interested, I used these 0.15 millimeter copper wire, which is just normal botch wire. That's the same stuff I use for prototypes circuits. This coil right now has a resistance about 217 ohms, and of course I will give it from an antenna cable. I will give it one of these, but I will use a smaller one because I don't want to have these. It sticks out too much, so I think a thinner one would be fine as well. And this time I also used the thinner ground wire because there's not a lot of current flowing. Of course, it's basically just a voltage that's applied and then that's it. There's not much current flowing, so you can get away with thin wires. Yeah, that's it. I will finish this sealing, and yeah, before I put it into its final rubber suit, I will be back and show you the end result. So I'm now busy disconnecting the high voltage lead here, and the way I do it is just simple. I have this is the antenna cable where I remove the shielding, and yeah, I just soldered it to the copper wire coming out here and just added a blob of epoxy And yeah, and after that I will rub some more tape around it. And yeah, while the epoxy was curing, I installed the first shield. That's the shield for the horizontal output transistor, very important. This shield has to be, because there's a copper plate underneath here, which is wrapped in tape to be insulated, of course. This has to be insulated from the horizontal output transistor and from the plate as well. And that's why I used some of these nylon screws. I just ran the nylon screw through here, and that makes it completely insulated from the rest. And the copper plate is connected to the ground here, and you can check this here. And the reason why it beeps very shortly is just because there are some caps inside the circuit, and they are charging up from the measurement voltage that is coming from the multimeter, because multimeters are only just applying a voltage and send a measurement current through to see if there's continuity. And as you know from your electronics school, probably you know a discharge capacitor is just short. Once it's charged, then it's not a short anymore. It's just an open circuit, then, and that's why it beeps. It gives you a short beep. So don't be confused by this when you do measurements. Just keep that in mind. Yeah, I think another layer of epoxy here is required, because it's they need to be just a little drop on top of these, and it should be fine. So I now got the other shield on, and yeah, it's grounded as well on this strap here. And yeah, this got this, it's I wrapped the final wrapping of office tape around, and it goes around here, and it already comes loose. The problem is if I wrap this very tight, and after some while it comes a bit loose, and that's where the rubber coating comes in. So because these self-fusing tapes, that presses the office tape permanently together, so it will not come off whatsoever. So this will be the last scene where you see you can see inside the coil, and yeah, everything looks good. Yeah, looks like this time it might actually work. So yeah, now I put the rubber around, and then we can try it. I'm sorry, no rubber fetish party today. Yeah, I had the rubber around it, but it turned out to be just too big, so it just didn't fit anymore. So I decided to give it some extra turns of taser, and yeah, hopefully we can get away with that. Yeah. It barely fits. No, it's okay. Yeah, it's again a bit too big. I think to make it smaller, there would be thinner copper wire required. So in this case, I must confess the copper wire I use is just too big. So there's a smaller size of these required, but yeah, I looked out for some online auctions, but it seems to be hard to get anything thinner than this. Yeah, I think we connect it up and try it. So it's all set up now. Okay, high voltage lead, selenium rod, right into the picture tube. The coil is grounded this time on the grounding step as well. I've put also a little plug there to have it unpluggable in case I have to change this or take it apart again for maintenance. Yeah, this is without rubber coating, unfortunately. Yeah, but I think thanks to the shield, this time is much better now than the last time. Last time this was only a foil, only a plastic foil as additional shielding. So this time we have the metal plate and the plexiglass. And here we have a layer of plexiglass and a metal plate behind. And in order to have even more space, I cut the horizontal output transistor. I had some pins sticking out there, standing out there, and I cut them a bit and shortened the contact, so that gives me an additional distance of 5 millimeters at least, I think. Yeah, this all wired up like I left it. Yeah, and I think this is pretty safe to give it a shot. I mean, in case you want to try it at home, I strongly recommend to get some knowledge about high voltage, because that is pretty dangerous if handled improperly. One thing for example is this coating here. This is some graphite coating. This is called aqueduct outside the picture tube, and the coating inside the picture tube form a capacitor. So that's the reason why televisions and monitors are so dangerous when they're switched off. If you take them apart right after you switch them off, there might be still some charge here. If you touch it from the outside, it's of course no problem, but if you touch somewhere here and get a connection between here and here, for example, that would hurt or even kill you. And the charge is what is dangerous, because it's immediately a real amount of power flowing through your body. It's like a defibrillator, and that's that's the thing that might kill you. So if you ever need to disassemble a CRT, let it sit for some hours to be safe, or just grab a screwdriver and a lead and plug the lead here and move the screwdriver carefully under this cap. Of course, an insulated screwdriver. Yeah, that's just a warning. I mean, you know yourself best what you can do and what not. Yeah, I have to switch that on, and yeah, it's always so exciting moment. Yeah, I already hear it working. That's no problem. The sound is just from this coil. So it's now at 12.8 volts, but it doesn't do anything. And I don't know why. I've checked it now several times and it seems all okay, except there's no high voltage. So let's get the 12 volts. So the power consumption is correct, and if I measure my high voltage here, I get 1.2 kilovolts, so that's way too little. And I made sure that these sits tight, so it must be some problem with my flyback. So I took the flyback apart and I can see no signs of arcing, so there's no carbonization or anything suspicious here. So what I will try now, I will mount it upside down. I will mount it exactly the opposite way and see what happens. Okay, it's getting exciting again, so I mounted that and turn the power on. 12 volts. And you can see a lit screen. So let's check the high voltage. Carefully. That's only 8. wonder why that's the case, because I have the full winding set on. .4. Okay, so any sign of arcing? I see no signs of arcing. But anyway, I get a lit screen, and what we learn from this is there is a polarity. Yeah, the reason for that, why it now works, is I reverse the coil, and so now I get the voltage exactly the opposite, and then it starts working because I get the right polarity here. And you might ask, by polarity, you might think that is alternating current. Sure it is. So in order to understand what went wrong here, we take a look at what a flyback transformer really is. So we have a primary coil, of course, a few windings, and we have something that switches. It's our horizontal output transistor. Could also be a FET or whatever. It's just something that switches, and we have a voltage of, let's say in this example, 10 volts. And of course we have a ferrite coil, ferrite core. We draw these dots to show the direction of the coil windings. So we have then a coil that has much more windings than the primary, of course. That's our secondary flyback coil. And then we have a capacity there, and a diode. This diode here is our selenium rod, and the capacity here is the picture tube itself. So if you have this picture tube cone here, I showed you the aqueduct on the outside, so that's your ground, and then you have the anode cap, which goes to the inside, and that goes to the inside coating, so that's your anode plate basically. That's your high voltage is coming out. So how does this thing work? I mean, basically what you get is some input waveform here. For the sake of simplicity, I just assume a square wave. Could be different because a flyback transformer is a fairly complex part. It does a lot of things in a television. It generates various voltage that are needed for the operation of the device. It generates the horizontal deflection and whatnot, and it's a very application specific part, and if that fails, so that's really game over. Then if you cannot replace it with the exact same part, then no chance. And yeah, of course, if you might make one yourself, like I do, at least partially, you have all these installation problems. So let's have a look how this thing works. So there are basically two cycles. So we have an on and an off cycle. So in the on cycle, let's say the transistor is conductive. The current flows through the primary coil, and we get a voltage of 10 volt here. Let's assume that this is 0 volt drop. Of course there's a little drop, and so then we have the 10 volt here, and that's just closed, and then that's it. So what happens then in this period is the current here is rising in a linear fashion, something like this. So when you switch on here, it's on, you get the rising current, and of course at some point it doesn't rise anymore. It's limited by the internal resistance of the coil. In a proper designed switching regulating power supply, you wouldn't let it come to this point anyway. And that's also the reason why it has, why it's an air gap coil, to have better properties there, to don't let it run too fast into these cutoff point. So anyway, so that's it. And it's switched on. It just switch on for a while, and then a magnetic field builds up here around the coil. Inside the coil, there's a magnetic field building up, and while that builds up, the current is rising. So in the next step, you switch that off. You have the off period, and what the current here in this inductor tries to continue flowing, but it can't. The transistor is open. And what happens instead is you get a reverse voltage. It's much higher, so it goes away. And so let's say we have 100 volt, this flyback voltage. So it's basically a little bit like a rubber band. You pull and then you let it snap back. Yeah, anyway, you have this off period now, so you got this flyback voltage here, the 100 volt, and let's say this ratio is times 10, so 1 to 10 transformer. You already get times 10, that's 1000 volts here. And that produces a current that flows through the diode and charges up the capacitor to 1000 volt. So these is in this direction, drives the, so this becomes a current, so it drives the current through here and charges up the capacitor. And that's then, when it's there, and the voltage is there, then it's already inside your picture tube and accelerating the electrons. So and I have to come back to the on period, because that's what I did wrong in the when I assembled my flyback transformer. You remember, it was just, the coil was just mounted in the wrong way. And so in the on period you have 10 volts here, and 10 volts times 10, that's only 100 volts then. So in the on period, when the transistor is on, you get only 100 volt, which is not much, by the way, it's in the other direction. And in the off period, when the flyback voltage is flying back, so to say, you get 1000 volts. So you get a voltage, you get something like this. So you have the zero line, so let's make a rough sketch here. So you get this your charge period, you get your minus 100 volts, so to say, get your plus 1000, and so it goes on and on and on. And yeah, if the coil is mounted in the wrong direction, the diode is wrong, and then this is what you get. And that's why we got these 1.5 or so kilovolts in the beginning, which was very little. And yeah, basically our huge peaks we wanted, they got completely ignored, because it was just the wrong way around. And that's the thing, and that's all also explained why the voltage coming out of the flyback is looking like it were DC biased, but in reality it's not. It's just because of this fairly complex switching regime that's going on here. So I hope that's now a bit clearer. There are a lot of tutorials and videos on YouTube about designing flybacks, flyback regulators and other switching power supplies. One I can really recommend is the Post-Apocalyptic Inventor. That's a guy that does really good tutorials, and I really recommend watching that to get a better understanding of this. So I stop here now. I hope that got a bit clearer, and I will now return to my video. However, it's 8 kilovolts, should be 11. I wonder why that's the case. I mean, it could be just. I don't think I miscounted the my windings. It might be just because I accidentally took the wrong way for the one or other turn. So yeah, really looks like I have to do another flyback. Yeah, it could be just like this. I had the arrow of course drawn on it and made sure that I do it as a correct that I did it correct, but yeah, maybe I messed it up. But we learned a valuable lesson here, and that's just that there is a preferred direction how you have to wind your flyback coil. So I'm happy I didn't destroy my monitor. So yeah, sadly this has to go into another round, so next weekend I will be here again and we'll do the experiment with another flyback. But this time, next time I will take thinner wire. I will try to order thinner wire on the internet somewhere. And yeah, I guess I don't have any problems whatsoever with arcing, and of course not with Corona. But I think that's just because I have no. I have not enough voltage to make Corona. Yeah, you see that? That's the voltage that's still on the picture tube after switching off. So get 12 volt. So now I switch it off, and yeah, 10, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's about more than 20 to 10 seconds after. Now I touch it with the probe, and most of the amount of voltage is gone. We still get the maybe that's the impedance. It sucks it immediately. It sucks the cap immediately empty. So the cap that's formed by the picture tube and the picture tube and the outer surface. Now when I can just come close, yeah, you see, that's not dangerous because it's grounded here, of course. I mean, it is dangerous, of course, but yeah, don't try these experiments on you unless you are experienced with that. Yeah, doing this high voltage stuff for a long time now. It was a major part of my childhood, and when I went to university, the first semesters I spent with playing with high voltage and frying things instead of learning stuff. Yeah, okay, well, yeah, I think that's it now. Yeah, we see each other next weekend most probably and do another flyback. So catch you next time.